a question. So you have a social network and there are n members and you're given a log file which has m timestamp. So here you can see that the times pairs of members, when you see it forms a friendship. So in this case, every member is a friend of a friend, and again is a friend of someone else's friend, again is a friend of someone else's friend. So it is well connected. So let's say the log file is sorted by timestamp, and as I mentioned, friendship is a relation. You can assume it to be an equivalence relation, like one is a friend of another and that person is a friend of another one. Now, given this, you have to determine the earliest time at which all the members are connected.
Sure. Okay.
Let's assume that you solve it in a brute force way. I'm not even asking you to go to a optimized approach. Let's begin. I think I should have given. Okay, you're taking the example. Okay.
Yeah, so I'm just trying to think of what the timestamps end up being. So I'm guessing that, let's say I had a graph of one, these are just the IDs for members, right? 1, 2, 3, and for the entire graph to form into a clique, that's what I'm looking for, right? It's all members are connected, so the graph forms a clique. That means that 1 is connected to 2, 2 is connected to 3, and 3 is connected to 4, right? If I were to add 4 into that mix, then that means that 1 has 2, 3, 4 as its neighbors, followed by 2 has, 1 through 4 as its neighbors, and so on, right? So I have a clique being formed for the graph. And so the input is supposed to be just a list of, or it's, m timestamps at which each timestamp gives me the, the connection formed, right? The edge. So 1 to 3 is an edge, I'm assuming.
Let's say, I think I forgot to give you the text file. Just a minute. Let me give you the text file, how it looks, so that you need not worry about the contents of it. Just bear with me. I think I should have explained you with the text file here. You can assume the timestamp to be let me give that example so that it becomes easy for you. Sorry, I'm formatting this for you. So you can think you were explaining me something. You can go with that explanation. In the meantime, I'll get you ready with this.
Sure. So I'm just putting the function
the text file here. This is the text file. This is how it would look.
Okay. Oh, so each timestamp only includes one edge formation, not multiple edge formations. Got it.
Yes. For now, you can assume that one timestamp there is one formation. Yes.
Sure.
Just assume that there is only one.
Got it. Okay. So in that case, in the very first one, I have an edge between ID 0 and 1, then 4 and 5. It seems like there's ID 0 to 9 going here, right? So in this example, the thing that I care about is that 0 to 9, those nodes all form a clique, right? Seems to be the thing that I'm looking for. So if I were to go for, a naive approach for doing this, what I should be able to do is at each step, I would make the connection, and then once it's complete, I would check all of the node members to see if they form a clique, right? But there's one problem here. It seems like there's no way I can avoid first doing an initial processing of the entire log file just to see what the nodes are, right? So when I first go through it seems like what I would want to do is do my initial scan, add all of the members that I find in, both the first column and the second column into a set, and then that's what I know what all of my pairs should be, right? So that when I try to check for a clique, what I'm looking for is to check that every other node is going to be a neighbor, right, of every other node. So
Yes.
figuring out if an item is a node, is a neighbor of every other item, that is something I should be able to do for each node in constant time by, writing my graph in an adjacency list form, right? Because what I should be able to do is for each node, just check the size of its neighbors, and the size should end up equaling the size of the graph minus 1, right? So what I have so far is scan entire logs to determine members, which is going to take me, m times, and then go through again, and each time add edge, and check for clique, which is going to be m times n, right? Is my separate step. So this entire naive solution seems to be m times n runtime, taking n times n space as well. Or not n times n, it's n times n. So one thing I should ask is, it seems like originally when I'm adding, my edges between each of the nodes, it doesn't seem like it's possible for me to re-add a friendship, right? For example, if I have 4-5, there's no way I can have 4-5 or 5-4 happen again. But I'm guessing the log file does allow that, right?
For now, you can assume that there are no duplicates. So
I see. If there are no duplicates,
the same friendship, yes, there are no duplicates here. If you see here, time pairs are given. At which friendships are formed. So this is one timestamp, and here friendship is formed between 0 and 1. Now, this has to determine the earliest time at which all the members are connected. So here you know that 0 to 9 are the members. So we need to know that they're all somehow connected, all 0 to 9 within some time. So we have to find out that earliest timestamp now.
Right. So if it's the case that there's no duplicates whatsoever, then it's always going to be that the only way you could have a clique form out of the social network is that it's after all m timestamps, right? If there are no duplicates, because by definition, if there is an edge that can be added remaining, then you haven't formed a clique yet, right? So if there are no duplicates, it would only way for there to be a clique at all is if all timestamps are processed. And at that point, you would verify whether the graph forms a clique or not, right? So
yes. But one thing you have to notice here, there is 0 to 1 here. There is a connection formed. And now if you see 1 to 2, there is a connection here.
Right. Yeah, I think.
And then if you see 3 was not at all called. 3 was not at all called. Like if you see, 3 was never paired up until this timestamp.
Yeah.
And also, so 3 was never a part of this group. Like you can assume this as a group. It was never a part of this group until it happened in this timestamp.
Right. So I think I misunderstood. So far, I've been talking about a clique, but I just reread what it said right now. This is not a clique. It says that determine the earliest time at which all members are connected, i.e. every member is a friend of a friend of a friend. So it's not that this forms a clique, like what I was saying on line 8 and 9. It's just that you don't have any node that forms its own, forest, right? It's fully connected.
Yes.
So that's very different from the approach that I was taking earlier. Yeah, that's the only requirement here is that each node has some connection. And then when you try to traverse down, you'll find that, you don't, whenever you traverse from any point in your graph, you can get to every other point, right? That's the only requirement for connected. So I take back the things that I was just saying. What I was saying here does not hold, except you'd still need to scan through the entire set of logs.
Sure. And if you see here, for this timestamp, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All of them are connected. So this is the earliest timestamp for us. Yes.
Yeah. So instead, it ends up being that we should be able to, what's it called? Instead of doing the clique check every time, what we should be able to do is, as we're going through, every single time we try and, the nice solution, right? Every single time you'd go through, you'd add your edge, and then you could perform DFS, right? And that would tell you that, I visited all the members or not. But that's still, a pretty bad solution, because DFS on its own is going to take you, big O of V plus E runtime, and then you're doing that n times, worst case, right? Which is much worse than m log n. Right, so improving on this approach, let's think about what we can actually do. So we start off and we have our initial empty graph. We decide to add the edge 0 to 1. That tells us that there is an edge between 0 and 1, and also that those nodes are visited, right? So you'd want to continue until potentially there are no nodes left that have to be visited. But even if you do that, you might end up creating two separate forests, right? So in the end, you just want to have one forest for the entire thing. Let's think about the typical graph algorithms that you have. So you have BFS, DFS, and topological sort, right? As traversals. It seems like you'd want to avoid running DFS at each step, right? There's no way you'd be able to run DFS at each step, because that's definitely too expensive. But DFS typically is one of the quickest ways to see if you have one forest. That's not true, actually. DFS is more useful for finding out if you don't have cycles, right?
Yes.
So
can you think of like you mentioned forest, and you mentioned about adding edges so that you can enlarge the created forest. So I'm hinting you, can you think of some minimal spanning tree kind of approach?
Yeah, that is
Kruskal's algorithm.
Right.
Or a union find kind of data structure.
Right. If you were to go ahead and, let's say, instead of going line by line trying to construct the graph, if you were to go ahead at the very beginning, would you be able to construct the graph and then do some operation? I don't know if that necessarily holds, because in order to find the earliest timestamp, you would definitely want to start off from the very beginning, right? From the very top, and then go through each of those timestamps one at a time, right? So partially creating the graph instead of the full graph. So Kruskal's algorithm is supposed to, I don't think it's going to take, log n time to run that. I think it definitely takes longer than that to get through. I mean, by definition, right? Because you're going through n nodes. So I'm not entirely seeing the relation to Kruskal's algorithm. But
like a union find data structure, would that help?
I'm not sure what that is.
Like union find.
Yeah, I'm not familiar with what union find does.
You're not familiar with the union find approach? Okay.
No.
Okay. Let's see. Okay. then
I know for Kruskal's algorithm, it's, you know, an approach you can take for finding the minimum spanning tree, right? But it's not clear to me the relationship, between finding the minimum spanning tree and finding the earliest timestamp, because you're not able to. I guess if you had a frontier, right, that seems to be the main relation. So at each step, you're adding a new edge to your frontier, right?
Yes.
And all you want to do is find out the earliest point at which your frontier has already encompassed all of the nodes. Okay, let's try and
without the union find, you can make use of, like, I'm just talking in terms of the data structure that you can use. Like, you read the log file and then you start performing some kind of union operation. Like, whenever you read one line from the log file, then you have, all that you have to look at is the two criteria satisfied, whether each member has a connection,
right?
And then
okay.
You can assume that there is one global root. From the beginning, you can assume some global root, and then from there, you will have a lot of not connected subnetworks with its own roots. Once you feel that this criteria is satisfied, then it means that all the members in the network are connected, and that's the timestamp.
What you're suggesting definitely sounds useful, because let's say when we start off in the beginning, so we did our initial scan, we have our set of items that we know we need to go through, and then inside, when we've processed 0 timestamps, we know that there's 0 forests, right, that we've gone through. But as soon as we go and visit 0, 1, that's one set, right? And we know that that is a single forest. And then we get to 4, 5, that's a separate forest, right? And these are both set items, right? So if we were to, let's say, keep these separate forests, next time we get to 8, 9, that's again a separate forest, right? And when we see 2, 4, we see that 4 has been visited before. So, you know, at this point, you have that this is part of the same set, right? Or
you can merge it, correct.
It turns out the more general thing we have is that 2 is a set, right? And because the set in which there's 2 and the set in which there are 4 are distinct, we merge those sets, right? That's the more general thing that we're doing. So that when we have 5 and 6 again, what we're doing is merging the sets. We have 7 and 8. What we see again is that we're merging the sets. And then finally, now we get 2 and 5. That's already been visited before, same set. We get 6 and 7, still part of the same set. But when we get 1 and 2, now we have another merge set. And then finally, when we get 0 and 3, you merge the 0 set with the 3 set. And you see that this set size matches the size of the graph. So this timestamp is where you have, you know, you've connected the entire graph, right? So if we were to do this in the most naive approach, I'm pretty confident it wouldn't be m log n time. So let's see how we can improve on that part. So when we're doing a search for, let's say, the correct set to merge with, right? That seems to be the thing that we care about, is how do we merge into the correct set? Because though doing a set lookup is constant time, finding a specific set is not, right? So let's think of a data structure that we can have internally. So I think internally we'll have to have a map, right? Which is going to map each of the numbers, 1, 2, 3, 0, and onward, to the set object that they're a member of, right? So this starts off that they're all part of an empty set, or they're part of none, if we want to make it simple, right? They're all part of none because they don't exist yet. And then whenever we first find an item, we'll say that both of the members, say, for example, 0 and 1, they're both part of the same set, right? 0, 1. They're both part of the same set object.
Correct.
When we decide to merge, this step is the part that seems like it would take, quite a bit longer. Because when you merge, let's say you have to merge 2 and 3 are both, 2 and 3 are both part of the same thing, right? So they're part of the same set, and then the next timestamp you see, it says that 1 and 2 are connected. So what that is going to end up meaning is that for all of these numbers that you have, you're going to have to update them so that they all post to the same set, right? So let's say that it posts to 1 and we update one of them so that it says 1, 2, 3, 0. But now this item gets updated by default for sure. So this one's also going to point to 1, 2, 3 because these point to the same object, right, to begin with. But now you have to update every single other item, right? So you also have to update the mapping for 0 and the 1. And at worst case, that's going to take n time to do, right?
Yes. So I'll give you another, like looking at the friends here, the friend is starting from 0.
Yep.
So it's kind of relates to some data structure. It is starting with 0 to 9. So it relates to some data structure. So you can track that in an
I see. Right.
array.
So I guess that's part of the constraints that I should have asked about. Am I guaranteed that the the IDs for the graphs are going to be in linear order, or like there's no gaps in the IDs? Oh, I see. Okay.
Yes.
If that's the case,
you can assume that there's no gaps and they always start from 0.
Right. Okay. If that's the case, that does change how I'd want to represent it then. Because initially I would assume that, this example isn't representative of any example. If I have a guarantee that 0 to n exists, in that case, I would want to have an array, right? To represent, say, what grouping this node is a part of. Let's see, how does that change it? If I were to include what grouping each of the items are a part of, it seems like I still, if I have this kind of map structure, I'm still forced into, doing an update every time, right? If I were to ever map a number to its associated grouping. So the reason that I use the mapping is that I can have that constant membership lookup, but if I have an array, I still have that constant membership lookup, right? In the sense that each of the indices maps to tells me whether that number is
number ID
exists, right? So let's say I have a none array of length 9. Let's just make it length 4 to begin to represent the number 0 to 3. So when I go through, I see 0 and 1 are connected. How would I want to update this? Let's see. If 0 and 1 are connected, one of my options was to have that set of data, but that's the exact same as using the mapping, right? If I were to update this to say that it's 0, 1, then 0, 1, this still has the same problem, where I say that it's part of this grouping. What can I do to avoid this? Let's see. I have the 2 and 3, and then the 2 and 3. Again, this is the exact same as the mapping. If I decide to update any of these indices, I'd have to update every other index as well, right? So because the kind of bound we're given is that it should somehow be log n, I know that the whole merging step should at max probably take logarithmic time, right? If I were to have some information that could take advantage of sorting, that seems like it's potentially helpful, but not fully. If these were to map to some grouping IDs, again, that seems the exact same as if I were to, have sets, right, associated with them.
Okay.
Actually, I guess, what's it called? When I think back to the sets, it shouldn't be true that, I have to update every set, right? 'Cause even if these are referring to distinct oh no, right, because I just have more fragmentation as it goes along. I was thinking that in the example that I just gave, there are 0 and 1, and then 0 and 1, and then 2 and 3, right? When I decide to do the merge step, the merge step is only going to take me one operation, or it's after I update this to have 1, 2, 3, 4. Oops, sorry, it's supposed to be 0, 1, 2, 3. When I update the second set, that's still I only have to update the set index 1, and the set index 0 is automatically updated, right? But
yes, only those which are like, you can use the log entry, like every log line that you are reading, based on that you can update only the relevant one. Like if it is 0 and 1, then you could update the 0 and 1. Yes, something on the lines what you're thinking.
I didn't follow that. I think we were just talking
let's
about
say you're updating 0 and 1. As you mentioned there, you're putting 0 and 1 there. And in your next entry, you're putting, let's say it was 2 and 3. So the first log entry contained 0, 1. And the second log entry, it contained 2 and 3. Let's say we had the nodes from 0 to 3 here. Now, 0 and 1, you have updated it here. Then you're trying to update 2 and 3. So you just put 2 and 3 here. And since you also maintain some kind of visited, like you can maintain whether have I visited any of these nodes earlier, something like that. And if you have visited, then you're sure and you just update the final one and then read out from there, like based on the last entry.
Okay, so let's say you're saying that 0 to 3 are the nodes, and then the next time through you add 1 and 2, right? So I think we were both clear on how the nodes are updated individually. For say when I add 0 to 1 and 2 to 3, but it's still the same problem. When you decide to merge, it's not, m log n time, right? It takes longer than that to complete. To do the merging step. Because as soon as I decide to merge, I have to go through much more than log n of the remaining nodes. I'd have to go through all of the nodes, it seems. Or not all of the nodes, but all of the connected nodes.
All of the connected nodes. I think for now you can keep that. That's okay. You need not to optimize further. This approach looks good. You can start to code with this approach. This looks good.
Sure.
Yes.
So, given our timestamps, let's say that I just have it in the form given above, where it's, say, an array of arrays. I'm going to say that our nodes is initially an empty set. And then for timestamp, start, end in timestamps, I'm going to add the start node and then add the end node in order to get our full set of nodes. And basically, I want to go through again, right? For timestamp, start, end in timestamps, I want to continue until it turns out that I've visited the entire set of nodes. So let's say that what we have is going to end up being our sets, right? So we have reversals or forest is equal to none for item in range, item in nodes. And so when we start, what we said we'd end up doing is checking for the associated forest for each of the start and end timestamps, right? So I think this could probably be broken down into a couple of cases, right? So the very basic one is that it turns out that the item is none. So if forest of start is none, in that case, what you would end up having, or if they're both none, right? And we can probably update these cases as we go along. If it turns out that they're both start and end are none, then what you would have is forest of start is gonna equal the set filled with start and end. Let's say that forest is gonna equal the set, and forest of end is also gonna equal this forest. Now the other case you could have is that it's a single item, and you're merging, and you want to add to an existing forest. In that case, what you say is elif forest of start is none, or forest of end is none. You can only have one of these as being none, right? Because the other case covered if they're both none. If only one of them is none, then you would want to add to the one that isn't none, right? If forest of start is none, we can break this into, instead of doing both of them at the same time, let's break this. So if the start forest is none, in that case, you would want to have forest of end dot add start, right? And then forest of start is going to equal forest of end, because you're just merging them.
Yes.
And this case is pretty much the opposite, where you'd have forest of start dot end dot add end, and then forest of end equals forest of start. And what you're left with is the case when you have to merge. So if you have to merge, this is the case where it seems like it would take much longer, right? Because what you're left with in this case is that you need to add every other item that exists in every single other item that exists in the entire other set. So it seems like what you need to do is for item in forest of end, you're going to say that well, I guess you only need to add it one for all of the items inside of forest. Forest of end dot add start, and then you'd also have that forest of start dot add end, but now these refer to two distinct objects, right? So that's the problem here, is that though you've updated in constant time all of the correct data, you don't have the underlying, condition that the objects that your items are referring to are the exact same thing, right? And that ends up being a requirement that they need to refer to the exact same thing each time. So the only way it seems that you could possibly do that is if you were to go through and say for, so before you do this, you have to do it, right? So you have to say for item in, for item in forest of start. So I'm saying that this step here on line 86, this is invalid. You can't do that. You have to, for each of the items in forest of start, say that forest of item is equal to forest of end. And that seems to be the only way that you can replace the underlying object, right? So let's say that forest of end is the object of 2, 3. and your force of start is 0, 1, right? Yeah, 0, 1. And what you've done here is, oh, this is still incorrect, and because let's say the thing that I'm merging is 1 and 2, right? All I'm adding here is the 1, 2, 3. But I'm still missing the 0, right? So really it's force. Oh, so I think the easier way to think of this is not that I'm adding start. I'm going to add force to end, right? And then force of start dot add force of end. It's so this is the part where this properly does the union merge, but it's super expensive. If I were to have this as a condition, I think it doesn't matter that they refer to different objects, right?
Yes.
I think if
For
this
now,
is
you
the case,
can go with the regular approach. Let's test it also once you are done.
Yeah, so this isn't complete. What I'd want to do is say that, if len of force to start is equal to len of nodes, then I can return the timestamp, right?
Yes.
Otherwise, if I go through all of the, I'm assuming that if I go through the entire set of items, I return -1, right? If it doesn't form a connected graph?
Yes.
Sure. So,
This is correct.
yeah, I think it works out to just, it seems kind of silly to have my, nodes as a separate set, because it seems like I don't really need that data, right? I can just have nodes is equal to 0, or really nodes is equal to,
An empty array. An empty array also would do.
0.
Because all that you're using is for calculation of the length.
Yeah, so it seems like instead of bothering with keeping track of what all the nodes are, what I'd want to do is instead of the nodes add and then nodes, oh, I have this all backwards. Force is supposed to be created below here. Yeah, I guess it is still useful, just because I can see what the actual nodes are when I decide to create the distinct force, right?
Okay.
More than anything, I need a count, but because the timestamps aren't in order, maybe that's not as simple to do. So cool. Let's print earliest connected graph, and let's go with the timestamps. Let's go with the example I had above. I need to update this. Cool. So I think that works out for the timestamps. And I know for this example, the output I should get is this one here, right? Unhashable type, right? I can't. Oh, strange. Start and end are supposed to not be sets, and they're supposed to just be values, right? So if I were to print start and end, I should just get values, not.
Oh, I think you printed in between.
Yeah. Yeah, so just get values, but instead I'm getting an unhashable type. So let's go back. This is line 84. I think it's 81 now. So force.end.add force.start. Oh, I think it's supposed to be, I think they have separate, because if I have a set, which is, I don't think add is a correct operation when I'm trying to merge sets. I think it actually ends up being union.
Union.
Is, 1, 2, 3. Let's see, y is equal to set of 3, 4. Union y, is that valid? Yeah, okay, cool. So union works out. Okay, so instead I got -1, which means that the length of force to start never seems to match up, right? So let's go ahead and just try and print off force to start at each step.
I think you printed, okay.
Okay, so it seems like I never finish off printing. I never finish off with the items.
Is it because you're adding that?
Sorry?
So 0, 1 you have added, then 4, 5, and then 8, 9.
Yeah, and then I have the 2, 4, and so the 2, 4 and the 5, 6, they merge together. And then I have the 8, and then I have the 5, 6, which gives me
6 merges.
Wait, the 2, 4 merges, and then the 8, 9, 7. I'm not sure how that comes out.
So 2, 4, 5, 6, and 8, 9, 7 came, which should have merged.
No, 7 and 8, that one still seems okay, because I don't think the 7 and 8 merged anything, right? It just added the 7 to the 8, 9. Then I have the 2, 5, which is still part of the same set.
But 6 and 7.
6, 7. Yeah, the 6 and 7 is the one that doesn't seem to merge correctly.
Yes.
Yeah, so the merge step here is adding to the end, I'm adding all the items from start, and then to the start, I should be adding all the items from end. The order here shouldn't matter, and I should get this exact same output here, and I do. So here I do get that, I should get that print start end. I should end up getting the 6 and 7 as what's being printed off here.
When 6, 7 came, it went and merged 2, 4, 5, 6. 6, 7.
Yeah, so the first merge was the 2 and the 5, which is not entirely okay. Yeah, that's not that wasn't supposed to be a merge either, right? It's part of the same set, but I guess when they do try and merge, it doesn't make a difference, right? Because those are already connected. Yeah. It might be helpful to print off force to start and then print force to end. Okay. See, it was the 2, 4, 5, 6 dot union.
Do you want to print before you are merging also, just to check? Like you're printing start and end. Do you also want to print just to check? Yeah, this would help.
Sure. It doesn't seem like it's really affecting it, but
let's see.
See, 6,
so
7.
when 2, 5 came.
Yeah, it seems like the union is not doing anything at all.
Yes.
Try that again and see what union actually does. Yeah, it should be.
Wow.
So
doing.
The one thing when I'm
maybe you should assign it back. I think you should assign it back. Try doing that, like forest of start equal to forest of start dot union of forest of end.
It shouldn't make a difference because what's it called? I'm modifying the underlying object, right? So if I do forest of start is equal to that, I'm changing the assignment, right? But if I'm operating on the I guess I see. Okay, union is I'm guessing I see. So union is probably not an in place modification. Right, because it's returning a value. I assume that this was an in-place modification, but it's not. So because it's not, yeah, this code wouldn't work out unless I went through each and every single item. Yeah, and unless I did this and then I said for item in forest of start, forest of item is equal to forest of start. This is the only way I could modify every single item. And now if I print, it'll merge out correctly, and yeah, it does.
Okay. Now it's.
But this is that linear. This is that linear search through that.
Okay.
Yeah.
Cool. It worked.
And it does seem to be the correct timestamp.
It is. Yes.
So for the actual complexity again, for this ends up taking big O of m times n, right? Just because this merge every time is going to take us n time to complete.
Yes.
There's definitely a couple of other cases I'd want to check for this, for test cases.
Sure, you can test for other cases.
The most basic of which is probably when we decided to, have 0 and 1 connected to at timestamp 2, we had 2 and 3, which ended up connecting the items in between. But this seems, for the most part, to be the exact same test case as previous. And, there's no real separate code path that we'll be running through here, right? Sorry.
Yes.
Yeah, so we look at the same time. What we really care about is if it's a non-connected graph, right? So instead of this, you want to have maybe an empty set as a test case, and you'd want to make sure that this one returns nothing.
Correct.
Which it does. You also want to have a graph that isn't connected at all.
Disconnected.
Yeah. So here we should also get -1, right? Cool, and we do. And for the most part, I think most other test cases would run through the exact same, branches, right? So I think this should be a pretty representative test set, and I think I'd leave that as, my kind of almost naive solution.
Yes, this looks good. I like the way you explained, like why DFS would take more time, and from then on we came to the union-based approach, which is good. I mean, this is a good start. I like the way you also put in all the test cases, like you thought about connected graph, disconnected graph, and empty graph. And you very well took care of the edge cases, and when union did not work as expected, you went through, debugged it. So you have a good debugging skill, so keep going. So most of it are the positives. What I told, like one negative I noticed, like initially when I gave the question, I think you had an assumption that you made. You rather assumed it as a click. I think you jumped a little bit quicker into the question. Other than that, I see that you're doing good and keep up the good work. Then I have a few more technical questions if you want me to ask. Like, can I proceed if you have time? Like,
I mean, sure. I definitely have time, but I imagine you'd want to end this at the 60-minute. So I guess these just follow up,
yes.
like about the same question. Sure.
Not follow-up questions, generic questions I will ask. Like even
Sure.
you will also get a brush up of your knowledge. Like, can you explain what is heap contention?
What is heap contention?
Uh-huh.
I'm not really sure about that, but I
Okay.
imagine that when you try to, just from the name, I
Uh-huh.
imagine what that ends up being is that when you try to access, a single resource, multiple processes or threads all aiming for the same thing, potentially you need to have some way to determine who acquires that resource, right? So there is some lock around the resource, and contention would mean that these multiple running processes are all trying to obtain that resource, and some of them get it and some of them don't, right? When they want to have access.
Okay. Okay. Sounds fair. Now I have another question. Like, what is heap fragmentation?
Heap fragmentation. So normally, whenever you assign items, you end up doing it into continuous blocks, right? So I think fragmentation usually refers, when you think of it, you think of it as disk. So you'd assign continuous sectors specific data.
Like, can you
when it comes to
write it here? Like, it would be clearer, like, if you could write it here and then explain.
Sure. So normally you assign disk/memory in a continuous fashion. It applies more to disks. If it turns out that you allocate memory and then you deallocate a bunch of memory, you have specific holes which aren't large enough to allocate data to fill those holes.
Like, can you explain with an example? Like, an example, like you take a chunk of memory that's allocated and then how a hole is getting created.
Yeah, so let's say, so I'm thinking of this more in terms of disks and not memory, but basically you just had some continuous sector. You assigned maybe a bunch of ones all the way through. Maybe it's filled with ones and then twos, and then another one, right? And now you suddenly decide to remove the twos and fill this with nothing, right? And suddenly it turns out that this isn't enough space to allocate something else meaningful in the future, right? So that's what the fragmentation could refer to, right? And so when you decide to do future writes across, you end up having to have a bunch of data allocated that isn't, set in a continuous block, right? You're going to end up allocating it in disparate multiple blocks. So maybe you'll have some data here, some data, and then, all the way down you have more data. But usually I imagine that this isn't too much of a problem with memory, but more of disks, just because when you try to, read from disk, it's always in a continuous format, right? Versus memory, if it's in RAM, you have, you can do lookups to it, right? You don't need to have continuous allocation.
I think heap fragmentation I meant in terms of memory allocation.
Yeah. So I'm not sure what heap fragmentation refers to on its own, but this would be my guess.
Okay, sure. How does garbage collector generally work? Like if you pick any language, be it Python or C or Java,
yes.
How does garbage collection work? I know few programming languages does it on their own and few doesn't do. But in the background, I just want to know how they generally work, how things get garbage collected.
Yeah, so the garbage collector is basically a separate running process within the, I guess in the case of Java, within the virtual machine, which is looking for, references to specific variables that don't exist, right? So whenever you decide to say, make some, int pointer x is equal, some alloc of some value, you end up allocating memory for that reference within the heap, and you say that its reference count is 1, right? And then as you end up allocating more things to, or not allocating, as you end up making more references to this item, you increase the reference count. And I think altogether it's supposed to be represented in a graph internally. Yeah, I believe that it is an actual graph internally, unless I'm wrong about that. But the more important thing is that you have these counters to functions, classes, objects, regular variables. And what the garbage collector wants to do is every once in a while go through and find items that no longer have references to them, right? And once it finds items that don't have any references to them, it's going to deallocate that memory, right, and free it up. And it's the process which it happens is kind of somewhat randomish in that you can't really control when the garbage collection will happen.
Okay. Sounds good. I mean, these were all the questions I had for you. So I think we are also close to the time, and I would wish you all the very best with your future interviews, and best of luck.
Okay, cool. I guess thank you for your time. Have a good rest of your day.
Hope I helped you a bit with your preparation.
Yeah, no, this is a pretty good question because it's not a common repeat, right? So.
Yes. Okay.
Yeah.
Cool then. Have a nice day. Take care.
Thanks. Bye.
Bye.